So today we'll take a look at this concept of torque, and going to be using it to play this game of balancing things on a seesaw. All right, so anyway, torque is basically a rotational force. So like say, for example, on the seesaw, when things are balanced, the torques are going to be equal on both sides of the pivot. So we're going to have a seesaw pivot in the middle, and if it stays put, if it's balanced, that means the torques are equal. So, and then so this we're going to be playing this seesaw game today. So to balance the seesaw, the torques, or the torque on both sides of a pivot must be equal. The torque on both sides. So the equation for torque, so this is like force, we get a net force. So we have a net torque is going to be the sum of all the torques in the system. The first torque plus the second torque must be equal to 0 for balance. And we're pretty much going to be working with just 2 torques today. And both of the torques could have multiple masses on each side. But we're going to be looking at just 2 torques. You know, one on the left side of the pivot and one on the right side of the pivot, and there could be multiple masses on each side, but that's the basic idea. So the first torque, for example, is going to be equal and opposite the second torque. So if we just take this equation and solve for torque 1, that'll be equal to negative torque 2. So we're going to be on 2 sides of the pivot, and left side and right side. So the equation for torque is basically force times radius. The force must be perpendicular to the radius, but this is our basic equation here. So on the left side, the torque on the left, we're just going to call it left force times left radius. It's going to be equal to force on the right and the radius on the right. So since we're going to be talking about just masses, we're going to be looking at their weights. So the force in question on the left will be equal to let me give it M1 GRL. And what this basically means, this is the weight. So this is going this force will be the weight of mass 1 times its distance from the pivot, and that's going to be equal and opposite, say, mass 2, its weight, and the distance on the right-hand side from the pivot. So the pivot's going to be somewhere in the middle, or generally in the middle, and then the term on the right-hand side is the distance of the mass on the right side of the pivot, and the term on the left is the distance of the mass to the left side of the pivot. So again, this term here is your force. This is what is known as your weight, as we have seen many times before. Well, these g's can cancel out, so you basically get this nice equation. And so this is basically mass 1 times the distance from the left side of the pivot, is going to be equal to mass 2 on the right side of the pivot. So this is the basic equation that we're going to be using. And for the sake of simplicity, we can make this a plus sign. So it's just going to basically be M1 radius on the left equals M2 radius on the right. And especially if we're just dealing with two masses. So this is our general equation, because we just want to get the magnitudes down, and then we can use that to play our game. So for example, let me go make sure everybody has that. Are you guys good? Still need a few seconds. Because now I want to go to PhET and get us started. Okay, 1 second here. Okay, so right now, why don't you guys go to this website, phet.colorado.edu. And let me just take you through just to make sure that everyone's here. Right, so you want to get here and go to simulations, physics, and you want to click on balancing act. Okay, you want to open up the simulation there. And let's go to the intro. Okay. Anyone not there? Because anybody? Still pulling this up. Is everybody there? So in order to play our game, because this is going to be the part here where we play the game, there's all the levels here. So hopefully we'll have enough time today to complete it, because I would like us to complete it in class. Also, you know, work together in groups of 3 and talk to each other, help each other out to get this done as quickly as possible, efficiently as possible. So for example, if I wanted to take a couple of these masses, they're just real quick. I'll take the 5 and the 10 just to keep it interesting. And I wanted to balance this seesaw using the 5 kilogram mass and the 10 kilogram mass. Let's say I just take this 5 kilogram mass and set it at say 2 centimeters. So let me just tell you something about this. So we're going to just assume that these positions are in centimeters. So this light hash mark here is going to be 0.5, you know, half a centimeter, and this is 1. This will be 1.5, 2, 2.5, 3, 3.54, right? And if it allows you to go here, I'm not sure, but I think it just stops you at 4. All right. So now, if I wanted to balance this, so 5 is, so here's my pivot right here in the middle. And if I wanted to balance this 5 kilogram mass, which is at a 2 centimeter mark here, where do you think I should place the 10 kilogram mass? Just on guessing or intuition there. Anybody got any guesses?
At 4.
So the 10 kilogram mass should be placed where? At 4. Is that?
Oh.
Okay, well, okay, let's just assess this real fast. So, okay, so this 5 kilogram mass is going to be at 2 centimeters. So 5 times 2 is 10. So in order to balance this 10 kilogram mass over here, where do I need to place the 10?
At 1.
At 1. So 10 times 1 is 10. Let's check him out. Booyah. There you go. So that's what we're going to be doing today, just balancing torques. Sound good? So let's go back to our picture. So you don't need to turn in your scratch work here, but this is just going to be helpful for you so that you can, get the answers right. So for example, on the left-hand side, I had 5 kilograms. Oops. And then the distance from the pivot would be 2 centimeters. So I'll just keep things simple. I can convert it to meters, but all right. And then over here, I had the 10 kilogram mass, and I solving for X, like where do I need to place the 10 kilogram mass in order to balance it out? And we solved that one already. There will be no notes turned in today. Just listen up, guys. Just you're anticipating a little too much. All right, so here's 10. Yeah, you don't worry about the units. If you need kilograms, yeah, kilogram centimeters. This is unimportant because we're gonna cancel everything out and get centimeters. Okay, so then this is gonna be 10x. So then 10 divided by 10 kilograms. Bam. Okay, that's gonna be 1. So x is equal to 1. And so you can write that down on paper just for your scratch work, and then go back and test it out so that see if the theory matches the experiment. And we've already tested it, and it does match. So 5 times 2, 10. 10 times 1, 10. All right. And so this is something that you can, play around with if you wish. So let's, and so for example, if I just go to the lab portion here, take the supports away, and put 15 at 3. All right, so that gives me 45. 15 times 3. Remember, these are hash marks. These hash marks are in the units of half centimeters. So 0.5 centimeters, 1, 1.52, 2.53, 3.54. Right. So I have to place another mass over here at some point to balance out this 45. So the easy case is another 15 and 3. Right, it balances out. And you can do multiple masses if you want to do that. So we could say something like 15 times 2, and then where would the 5, like if I chose 5, where would that have to be placed in order to balance this 45?
At 3?
Yeah, that's correct. That's correct. So, and again, if you don't have to, guess about it, you can actually put it into the equation here and test it out yourself. So, for example, there's only one mass on the left-hand side, and there's going to be 2 masses on the right. So I have, say, M1 RR plus M2 RR. Its distance, you can say R2R, whatever the case may be. All right. So on the left-hand side, I have 15.
Wait, Mr. Kelly, we can't see what you're writing.
Oh, I forgot to share. Sorry about that. Okay, so on the left-hand side, I have 15 times 3. That gives me 45, of course. And then I place the 15 kilogram mass at 2. And then if I chose a 5 kilogram mass, for example, and I have to solve for X just to make sure to figure out the distance I have to place the 5 in order to balance this out to be 45. Okay, so this is 45 over here. This is 30 plus 5x. So 45 minus 30 equals 5x. All right, 15, 5x, and you know x is equal to 3. All right, that's your theory. Match it up with experiment. So it's 15 at 2, 5 at 3, and look at that. We have balance. And if you want to, you can put the level in there to make sure it's roughly level. And then if you want to have the forces labeled just to give an idea of the magnitude of the forces, that's up to you. So that's just the gist of what you're going to be doing today in the games section here. So are any questions thus far? But yeah, that's the main deal there. Let me just go back. So yeah, so in that case, we have the two masses. We're balancing torques. This torque over here has got to balance the sum of these torques over here. 45 must be 45. And one other thing I want to mention about the torque equation, it's not going to be that important for us today, is that torque 1 is going to be equal and opposite torque 2. So it's the torque on this side is always going to produce a clockwise rotation. So if we look back, so if I took this guy off, he goes back. And if the system was just under the influence of these two masses, what would happen is that this entire system would just continue to spin clockwise. And then vice versa. I had this guy over here. The torque on the left-hand side would continue the system, rotating the system counterclockwise. So counterclockwise torques are always positive, clockwise torques are always negative. And so that just gives a little bit more relevance to this equation, because this is essentially what it should be in reality. So this is going to be a clockwise torque, a counterclockwise torque on the left-hand side, and a clockwise torque on the right-hand side. And this will cause this, it would cause the system to spin from right to left. This is a clockwise torque, and then this guy would go from left to right. That's a counterclockwise or positive torque. And this would be a negative torque. But that's just something, neat to know just on the back end. You don't have to use it in the context of our game today. So let's see. So make sure you have this basic equation here. You can do your own scratch work. You don't have to turn in any notes. Let's see if we can get the answers all good. All right. So let me move back over here. And I want you guys to do all the levels, right? And let's start off with level 1. So it's going to be some, parts here, different parts. And this guy here, he wants you to balance the system. So we have 10 kilograms at 3 centimeters, 3 meters, or it doesn't matter, 3 units. So this is going to be a torque of 30, right? And so then in order to balance this guy, it's very simple. Got 10 over here. So you're going to place them at the 3 mark. So this is going to be 30 and 30, equal and opposite. And you can check it out. And there you go. All right, so that's balance. So that's pretty simple. Now, these are nice. What will happen with this configuration? So this is 15 and 1.5. So maybe you want to break out your calculator. You can do it in your head, whatever. 15 times 1.5. That's 22.5. So 15 times 1.5, 22.5. And then, so that's the torque over here, 22.5. And the torque over here would be 20 times 1.5. And that's going to be a torque of 30. So this torque is going to be more than this torque. This is 22.5, this is 30. So it looks like this is going to happen. Have a clockwise torque. The net torque in the system is going to be clockwise or negative torque, and it's going to cause it to rotate from right to left if left under the, if it was allowed to rotate all the way around. So that was that's what you do there. And then 5, I'll just do one more and I'll let you guys go off to the races. All right, so then, so the pivot here is usually in the quote middle there. So this is 5 times 1, 5. And so where should the 10 be placed in order to balance this system? 5 times 1, 5. 10 times what is 5?
On that first half centimeter.
First centimeter or the half centimeter?
Half centimeter.
Yep. So the half centimeter, we'll place them here and good. See how that works, guys? So you want to do all of the levels, level all the way up. And by level 4, it's going to be multiple masses, like 2 or 3 masses on either side. And all you got to do is just manipulate this equation for however many masses on the left or the right in order to solve for x. Okay. So let me now get you to your breakouts.